All right, cool. So thank you for coming for this short paper talk about this is the FPT paper from last year, GraphNoC. So just quick background, what they're tackling is with networks on chip or NoCs. So these are dedicated hardware to transfer data where they treat data as being sent in packets. So the kind of the advantage of NoCs is that different traffic data can share the same wires, and then you would have routers in between that are responsible for forwarding these traffic packets. So it's more scalable than NoCs. If you can imagine, once you're kind of allowing sharing of routing resources, but one of the downsides and trade-offs is that sometimes this is now non-deterministic. So NOCs are pretty susceptible to congestion and how much traffic is actually going through each of these routing resources. So with FPGAs now has these hardened designs. They allow, but they also allow tuning and designing the NOC design. Um, so a lot of optimizations being done is to pretty much design the NOC maybe for a particular application that you're targeting. So how do we tell how good a NOC design is? Is that we would need a measurement for the worst case routing latency. And by worst case, we're referring to because of that sort of non-determinism, you need to figure out what's the basically, yeah, what's the worst case that would happen. And so, as this paper pointed out, there's a few ways you can measure worst case latency. The simplest one is you just do full RTL simulation. So as I mentioned, this is pretty slow. FPGAs are fairly large designs. So, and the issue is with optimize if you're doing design space exploration with the NOCs, you're iterating through probably thousands of designs. If each one of these takes tens of minutes to predict, then this really adds up. So what they're focusing is like they're pointing out there's a gap here where we can do some speed up. And so other ways people do is with analytical models. That's also what you do is you either use some sort of cost function, uh, or in this case, what the paper showed is you would have a network. The one of these uses network calculus. Basically, you use mathematical functions to calculate the worst case latency. The limitations that they point out with these are some of them are application aware, but they would only apply for certain NoC architectures. So if you want to do design exploration or do a little bit of perturbation, these models don't really apply. There are other ones that are just not application aware at all, but the nice thing about them is they can provide a static prediction uh, on the latency. So what you do now is, well, we have all this data, so why don't we try using ML? That seems to be everyone's approach right now. So you have two ways of going with this. One is with conventional neural networks. So you can think just a feed-forward network, or technically you could even do convolutions, or you could use graph neural networks. So what the author goes into is motivating using GNNs over other types of neural networks. So one of the limitations again with neural networks is we can start with thinking about what's called a non-Euclidean topology. Basically, think with a torus shape. If we have a NoC topology that's connected in a torus shape, so this is think like a 2D grid, but then all the edges are wrapped around and connected. So what you have is like a kind of, if you think in 3D, you're pretty much doing a circular loop. So something like this doesn't really work with traditional neural networks. So if you've looked at how those architectures are designed, you need to flatten inputs. There's no way you can do 3D shapes. Yeah.
Do you mind if you just move Alex to the top
Oh yeah,
or shrink
sorry.
him or something?
Yeah,
Uh,
sorry. I
thank
realized I was covering. Yeah, so So once with something like that, when you're flattening into vectorized inputs, you're losing that wraparound connectivity info. There's no way you can represent that original connection. So that applies to not only the switches, but also if you have some sort of traffic that wants to utilize that edge, there's just no way to represent that. So they've also shown that with so ANN is just like a simple feed-forward network using 9 layers and 1024 embeddings. So that's fairly large. And then on a 4x4 torus shape, that the training loss plateaus, what that means is like it stops learning. So they're showing kind of a limitation with neural networks, and then bringing in why graph neural networks might be a good choice. So on basic level, graph neural networks, the advantage is like you're encoding the graph into the input. So the training is basically done. You're letting the model learn about what the graph looks like, how it communicates, or what communications are available. So what GraphNoC has done is you do a hierarchical encoding. So you start by encoding the switches. So on the top right here, I'll try to cover this one up as well.
Like hide floating meeting controls.
There we go.
Yeah.
Okay. Uh, so they tackle a few. I'd say they targeted two NoC architectures. Each of those they let it have variations between choices of two switches. So they would mix and match and call these different variants. So you can tell with what you first do is with the top graphics, you're encoding the switches. Uh, Basically, the directional nodes, the NWES, that's just for representing like hops of directional ways you're going. And then, or if you go to the P, the processing element, uh, and that can do like represent like some sort of traffic that would actually go into the computation unit part. So then you would encode the NoC topology. So that means you're building. This is where the kind of the design space exploration happens, where you connect up these switches in a way based on either existing architecture, or if you want to modify it, that's where you would do the modification. So that's in like the thicker black lines. So you can see this is basically a torus shape. You would have the 2D grid connected, and then you would wrap connections around. Uh, so the last part is to overlay application traffic into the graph. So what they use is what the orange part represents. So in this case, this is a singular NoC traffic flow from the P unit of the 1 0 processing element. It comes out, and then it's going to the P of 1 1. So this would be for this, you can think of this as one sample. This would be one sample of the training. You would have this one application layered on top of it. And then if you batch it, then you can have multiple traffic overlaid on top.
Let's just repeat this back to you. So, okay,
Yeah.
lowest level, you take the actual switch, like the crossbar, basically, like
Yeah.
you got a P on the one in the top left, for example. P can connect to the south.
Yeah.
The west can connect south. The east can connect to some central node, which can connect to west. Okay, so that's the switch architecture. So they don't have a full crossbar there. They have some
So it's sort of
unlimited connectivity.
yeah.
Then they encode more edges, which give you the graph topology, as you said, like so this is a torus.
Yeah.
And then you add, so that's all architecture. Now you add in the application traffic.
Yeah.
By putting additional nodes in connected to whatever, let's see, PEs they're connected to. So that big red node is connected to, those are the source and sink PE basically.
Yeah.
Which in that case are right beside each other, but these could be all the way across the the array, I guess.
Yeah.
Okay.
And yeah, so this is all of this encoding is basically just the input for the model to learn. So the model will look at samples of this full graphs, and then it can learn. So that's the interesting part where you can feed it different NoC topologies as well, and it will somehow it should do like a aggregate learning across different types of well, I guess architectures in that case. So yeah, so for clarification, this wasn't really mentioned in the paper, but this is my understanding. So they're not fully mixing all four types of these switches because BFT and Hoplite are two NoC architectures. So what they've done is they train a model to handle Hoplite, varying Hoplite BP mixing with Hoplite buff switches. That's one architecture. And then BFT-T and BFT-Pi switches are found in a BFT NoC architecture. So they would vary those as like for like different designs. So and just for reference, Off-Light BP is like I believe it's like a buffer based switch, whereas like, oh, sorry, Off-Light BP is like a back pressure based FIFO switch, not architecture. And then Hoplite Buff is like I think like buffer based.
This hoplite, I mean, the original hoplite actually didn't have significant buffering. They did
Mm,
is an unusual design. They did what they called deflection routing, which is basically you try to go to, say you're going from the west to the east, right? And let's say the
mm,
east port is busy, like you lost arbitration, the PE tried to send something in instead, right? And let's say
mm.
the PE won. Or is there another connection I can use that make this even more clear? I'm not sure. The original hoplite, though, like if you didn't get to send it to the east, you actually deflected it. You just sent it north.
Oh,
It doesn't want to go north. This is like a
yeah.
TTC algorithm, right? Whatever, it's going to send you north. You just loop around on the north, so you come back and you get try again. So
Mm.
it's worst case latency. It was
Yeah, it'd be
terrible.
very good.
If you didn't have too much traffic, then they showed that resource cost is low and the latency was acceptable. So I don't know if that's what the original hoplite
Yeah,
was. I
I
don't know
think
what the
these are both like so I believe like one of these two are ones from a 2020 paper and one from a 2022 paper. So I
yeah.
imagine it's
Okay.
different, very,
I'm almost certainly added buffers
yeah.
within the name, and that's a more traditional design to have buffers.
Mm.
Yeah, okay. So do you think BP is back pressure?
Yeah, that one's like a back pressure design.
And is somehow back pressure is enough that it doesn't deflect or something? Okay, I just don't know.
Mm.
Or maybe they changed it and then renamed the
Maybe, yeah.
deflection one. Okay, and then the BFT is butterfly. Is that what
Yeah,
that stands
butterfly
for?
flat
So it's
fat
basically
tree.
a tree. It's a
Yeah.
flat tree. Okay. Uh, and the different, I'm not sure. So two
Uh,
different topologies, like the
yeah,
power one
apparently
is that
they
some topology
yeah, apparently the main BFT architecture mixes these two.
okay.
No. So yeah, I want to point out something interesting here is like between BP and Buff, they look exactly the same in terms of connectivity. In fact, they are the same. So the question is probably like, well, how do you differentiate this? Well, the thing is with machine learning, it's a bit of a black box. All you do is tell the model that these are different switches. So you would give it some sort of switch attribute. And then as long as your ground truth generation from either an analytical model or RTL simulation has like a different answer in terms of routing latency, then you kind of assume the model will be able to figure out like a difference. So when it sees that attribute laid out in a particular way, then there's some sort of pattern there. So yeah, so for the model overview, quickly, it's just that all that graph we saw initially, that's what you input into the model. Graph stages and algorithm, I'll talk about in the following slide. So that's where the main learning happens. And then they follow up with they combine a classifier and regression layer together to do prediction. But it's basically it's just regression. The classifier, I think, is it eases like the regression complexity, but overall it is still a regression task. So you're predicting a continuous value. So for graph stages, this is a iterative algorithm. So during model training, at each iteration, adjacent nodes will exchange information with each other. So these would be the node attributes, which are set of weights that these are parameterized. You can decide on how much or how you want to set up those. And the idea is like after an iteration, they would combine the messages they receive from its neighbors and get its own updated representation. So the simplest way to think is just a sum of weight times some sort of learn weights and activation. So this makes a lot of sense for social networks. That's like a way to, in this case, what you're seeing on the right is basically after training, this is what you would probably ask or Alice, the relation between Alice and Bob based on the learning process.
We just read that last equation. So you've got xv1 new is the aggregation function of it was xv and the other three nodes. So you do take
The
your own
adjacents, yeah.
Yeah, okay. So you take your own representation into account, which makes sense. So
Yeah.
and then plus nearby ones. Okay.
Yep. And then for the prediction stage, so what they're trying to do with this model is you replace the uh, predicting worst case latency with a fast GNN model that just outputs a value that would be faster than RTL or analytical models. So what they're doing with the kind of separating into classifier and regression and then merging it at the end is the classification module predicts a bucketed score, and then a regression predicts a more precise score inside the bucket. So the equation here they give is I'll explain it with the graphic right after, but you can think of resolution, basically how many classes there are, and then you have that regression prediction, the reg. So that's like a offset from within that classification. And then this oh sorry, well resolution is a size, yeah, the size of each bucket. So like maybe 1 to 200 in terms of score is one bucket, and the number of total buckets you would get, which is the number of classes, would be the highest score divided by size of each bucket. So as an example, suppose the limit is 400, you have a resolution of 100, then you have four classes. The classifier would predict the more coarse class. So it'd say it'd be the 200 to 300 range, and then regression would predict the offset and for like a more precise score. So I believe this is just to reduce the number of parameters. Regression is a bit more, you'd probably have a bit more uh, parameters to it. Um, I imagine this is something that they found through experiment. It's not really mentioned. They kind of just presented it.
So they don't really like say this is how we did this. Yeah,
No, this
you're
is
right.
not.
This does look like just essentially regression, but in two pieces.
Yeah,
Right. So
I haven't seen this method before, but yeah,
hmm.
they kind of just presented it as is. So for experiment, they trained three GNN models with different sizes. So they have like the 1 million parameter up to a 7.7 million parameter model. So here you can see these three are separate like categories as well. So each of these they train three GNN models. So this is before. Later on, I'll talk about like they also do like a foundational model, which means you let it learn different graphs at the same time. So here, this is done separately.
Oh, okay. So each of these models is fine-tuned to one
Yeah.
architecture. Okay.
So for the hub buff and BP, you have 500 variations. This means in like the given size, 3 by 3 up to 7 by 7, you would have each slot will be either a buff switch or a BP switch. So that I think that comes out to 500. Don't check. So there for ground truth, what this means is how do they generate the actual like golden result? So for Hoplite, Buff, and BP, they use I think Hoplite has an analytical model, Hoplite RT, I think it's called. So that's what they use. For BFD tree and BFT XPAR, these are done with RTL, so full simulation. And in terms of result they presented, I think this result isn't too interesting. But basically, they measure in two ways. So you have what's called delta K. That's absolute difference between your result and the prediction. So for delta 5, that means your prediction is within 5 values of whatever your measurement is. So here, ground truth latency, if it's predicting 80 cycles, or sorry, if the ground truth is 80 cycles, prediction would have to be between 75 and 85 to be counted towards that. And then you have top K, which gives it's a percentage, so a relative difference. So for 80 cycles, it'd be that 4 cycles would be within 5%, so it'd be 76 to 84. So if you look at, you can clearly see like for smaller models, I'd argue it doesn't perform too well. It depends also, yeah. So if we look at top, uh, in terms of 20%, so that means almost all of their prediction falls within 20%. But then when you get to narrow 5%, that's where you can see like, I think these results I think the large models are decent. The smaller models, you can see it's clearly not enough. It makes sense for uh, and I think this is the aggregate of all the previous setups I showed. I wish they separated a bit. I'm curious to see for like larger larger topology if they could do it by category.
I do find this is a sort of a odd way to present the data. It's like a regression that you're then bucketizing and presenting percentages within these buckets. You could do like a correlation plot and have, mean and absolute error and so on, right? So
I think it's usually they would just do top 5 because that's like I think it's like a nice balance.
This isn't really a
Oh
classifier.
yeah,
Do you know what I mean?
yeah,
Like,
fair.
yes, they're doing top 5, but it's because they're taking it. I mean, it just seems weird. Like, this is actually a regression where you have like a
Yeah,
floating point value that is your ground truth.
they should just do like yeah, like a
Uh,
error
Yeah,
percentage.
usually, I mean, this is an error metric, but it's kind of
Yeah.
this digital error metric in different buckets, which is a little harder to interpret. I don't know, maybe you could do it as an adjunct to the other one, but
Mm.
like a 55% top 5 is a bit hard for me to interpret. So
Mm.
it
Yeah,
means, yeah, 55% of the time I'm within plus or minus 5. But
it's
it's
something.
in,
Oh, sorry, Vaughn. Something I also find strange.
with tolerance, like
yeah,
five.
no, I understand what the numbers mean. I just find it an interesting way.
Yeah.
Is this common in
Yeah.
regression? I mean, for classification it is, but to be honest, this isn't really a classification problem.
I checked. There's no such terms like in the regression studies. Probably they named this delta K top K like uh for this regression task.
Yeah.
It's really weird term.
Yeah, usually it'd just be like like a absolute
Yeah.
error percentage.
Yeah, something that I
Sorry,
find
Alex.
So
Yeah, go ahead.
yeah, something I find strange about this is that their training accuracy. I'm looking at the top 5 for GNNM and GNNL for both top and delta. It seems that their test set often does better, or at least for the top 5. And I think that's a little strange. I just would expect the training set to have a better performance than the test set, because by definition, you trained on it. You should have a better quality. It's just something that I find kind of odd.
Yeah, I think that's fair. Maybe they didn't push too far with the training. That
Maybe.
probably is all I could think of. And also, I guess I do wonder like summarizing all of this together might not be the best if they're separating like into different models at this
Mhm.
stage.
It's predicting latency. So
Mhm.
in an application, there would be a lot of different latencies, one for every flow. So is this taking all those latencies or what is it?
So I think this is like complete. Yeah. Oh, sorry. This one's is just for that hoplite
What I mean by
variation.
that, no, I don't even mean like for hardware. I take an
Mm.
application. It has a whole bunch of like, we go back to your graph.
Yeah,
There's like a red line. Yeah. Go back further. Yeah.
like
So
this
you
one.
have that red one, but in a real application, you'll normally actually have a bunch of traffic flows. So you'd have a bunch of those type of nodes. So when they do accuracy, are they getting the latency for each one of those things? Or are they getting the worst, or what are they getting?
So I believe it's worse for this full application. So you would
The
have all the
worst.
traffics on here, and
So you get
it
the
predicts the
worst
worst.
latency of all.
Yeah.
Essentially, it's a lot less information than you would get, for example, from an RTL simulation, where you would actually get
Yeah.
it for you would get the distribution of latency for every traffic flow.
Yeah.
And that often is necessary. Like to actually know how well the application does, just getting like what was the longest latency if any traffic flow is not enough.
Mhm.
So
I think this could tie in with their experimentation after this. So what they did next is saying, well, the goal of this gen is like you replace that iterative design exploration part for the NoC. So let's assume you're given a particular application. We want to generate a best NoC design that minimizes possible routing latency. So they fix it with a 4x4 topology. Each switch uses either hoplite buffer or BP, so you have 2 to the 16 possibilities. They start with, let's say we're just using the GNN. Each epoch, you would take 128 variants. By variants, I mean you do like a pattern of buff and BP setup. So maybe like full buffs, 4x4 only buffs, or 4x4 only BPs, or like a mix of intertwine of that. You'd predict their latency, then using the GNN model, you select the best one as a base, and then you generate another 128 variants off of that. And then you repeat this for 100 epochs. They take the best NoC design and then they feed that to the analytical model to get ground truth latency. And what they noticed is that the GNN regresses latency by about 20 cycles. I forgot the percentage. I should put the percentage on. But their argument is like it speeds up compared to the analytical model for just that one run by 30 times if they run this on run it on GPU. But in terms of result, what they've done after is they noted that the best way is to use the GNN, but then with the time you save, you still run the analytical model near the end. So after the 100 epochs, you would take the best model, but then you would swap over and use analytical model to choose the best variant and then generate the multiple variants again and do that again for 25 extra epochs. And in this case, they claim that there's no regression in cycles. The speed up for the total time of this happening is about 3 times for GPU. And so I think this is probably like a case where, yeah, I think the GNN model probably doesn't have enough information. It's also, yeah, I guess they're not learning on everything like a analytical model or like a RTL can provide.
yeah, so again, like this, they're taking just the worst case latency of anything in the whole application, basically.
I believe so, yeah.
It's interesting. It's not exactly throughput, so
So the last experiment they did was kind of testing the possibility of having foundational models. So what this means is GNNs are supposedly multi-model. That means you can have one GNN that predicts latency for different types of NoC architectures, as long as your data set has enough diverse data set. It could technically even predict ones that you never showed it. So they didn't do that. They didn't experiment with that. But what they made an argument of saying, well, okay, let's train it on 2 types of architectures, which they argue are really different, and they look at how well it predicts the latency. So in this case, they're saying like so what this means is the distribution is for their data set. This is a data set. The distribution of latency. So for each latency, you mark how long the latency is in cycles, and how much percentage of the data set is that particular latency. And they're saying like it covers well even for in these 2 cases they're basically saying BFT tree's latency is very different from half-light latency, and it does well to predict both of these. So
I
that's
don't
what
know if I understand what this is. So they trained on hoplite and they're showing you the prediction accuracy.
so they train on both.
They trained on both, then they show that
Yeah.
hoplite is accurately predicted, and then they
And BFT tree is also accurately
but
predicted.
they trained on both, so that doesn't
Ye-
actually prove that it's a foundational model that can
Yeah,
adapt to a new one.
so
They're just
that's
arguing that it can cover two different things.
yeah, they're saying if there is more data set, then potentially you can cover more.
It seems like a fairly that like they're saying because we covered these two things, but they gave it categorical information, I think, about which one, like or which switch design they're using, that they could therefore do other things they've never seen. Is that right?
I think so, yeah.
Oh, okay.
Yeah,
Interesting. I mean, that does
Alex, go
seem
ahead.
like a not well-supported conclusion from the data. Like, because there's just two different things, right? Like one is, can I match the things I've seen? And then now can I match something I didn't see? Interesting.
Go ahead, Alex.
Yeah, I just had a quick question. I'm just trying to interpret this graph. I'm not familiar with the axes. So percentage is the y-axis, and the what is the x-axis?
X-axis is the latency, I believe,
Is each of these like a different, so that's the worst case latency in a different
in
application graph,
yeah,
application architecture pair?
very pair with the variant of the topology as well.
Yeah, so
Yeah,
it's in Hoplite, but you have different topologies for Hoplite. You also have
with
different
different applications.
applications.
Yeah,
Each of those
so it's like
become 1 point.
yeah,
And you take that whole thing, consider it a probability distribution function, and you graph it, right?
yeah,
So you get like 1 point for every application architecture pair that you're going to look at.
Hmm.
Okay.
yeah.
Okay, I see. That makes sense.
I think, I mean, I was had the same question of what do the graphs mean, but okay, that answer seems logical. So
I guess you can say like it's saying like let's say this point, 6% of the data set, their the worst case latency is this value
yeah,
here. And then
yeah,
yeah, and then the orange is the ground truth prediction or ground truth latency, and then the blue is the predicted latency.
yeah,
Yeah. So they're saying it covers a wide range of latency, basically.
yeah.
And that's why you say it's like a CDF or a PDF. Is it a PDF or CDF? I think it's a PDF. It's like a PDF, so it'll add
Yeah.
up to
It would be a
100%.
PDF,
Yeah.
So if you take the integral of this, you get 100%. I get it now. That makes a lot of sense.
Yeah. Uh, yeah. So yeah, I'd say this part is more like uh just like I think it's like open thought kind of.
I was a session chair for this session, so I actually asked the speaker. I didn't want to ask him really aggressively because we're actually in competition with the professor, and I only read half the paper, so because I didn't have time before the conference. So, but when he mentioned like they could do other topologies, and what are the odds that you kind of overfit, and you predict these well, but not others? And he said,
Yeah.
"Oh, overfitting is never an issue nowadays." And I thought that's a really weird answer, right? It seems like that's always an issue. Like you give it a big bucket of data, you fit it well, you always worry about what about things that are out of distribution. So anyway,
Yeah,
but it was like, it does seems like a very odd answer. So
I also
you
remember
did it with a
that.
great deal of confidence. I was like, that seems strange. You're oddly confident in it, but so
Yeah, I agree, Vaughn. I had the same question. That's why I find it odd that the test set is so close to the training set. This is how you can tell over prediction. And when he said there was no concern, I'm looking at the data. He's right. There's no concern in this data, but in general there is concern. So I don't know. I also agree.
yeah, I don't think I fully understood it, but it's like hard to like. Well, it's basically like if you go out of distribution, it's like how
Yeah.
broad is your
If you
distribution?
bring in like a new topology,
Yeah,
it
like
might
you
not.
say, look, this is my predictor for this size of hoplite, blah blah blah, network where I only care about now worst case latency and so on applications that look like this, then you can make a strong statement of I'm confident I got that one right. But yeah, then you have to be very careful that your statement is only about that. So
Yeah, I'm assuming like in this case, the argument would be like within the same size, like it's capable of handling like at least two different types of architecture. But I guess in terms of result, that's probably as far as you can say.
yeah, I
Yeah,
think
this
to say
rest is
it's predictive
speculation.
for the architecture, that's like a significantly different architecture that was not in the training set, significantly different applications. So
Yeah. Uh, so yeah, that's actually all I wrote down. I think.
It was cool. I think actually your technique of making slides is a good one. Maybe I should copy that someday if I ever have time. Instead of stream of consciousness.
Yeah. Yeah. Are there
Oh, wait,
any?
I'm still a bit confused.
Yeah.
So does this like graph neural network like only predict latencies, or does it also like do anything else like
No, so this would just be like a value of latency yeah. That's it.
okay.
Yeah. And that's sort of how we're using it right now, except we're doing it in terms of like a cost. Maybe fun to talk about what we're doing with sort of this sort of GNN approach as well. So for us, uh pretty much instead of varying the design, we're fixing the design, but we're saying we're changing the traffic flow overlay. Which in the future I think it'd be more interesting if we start varying the design as well like this. In that case we could batch it. One of the challenges we have right now is like we can't really batch inputs because it's done during simulated annealing for that particular placement.
I guess you can batch them during training, but you're saying you can't.
Yeah,
batch
we
it
can batch it
during
during inference. Yeah.
The only way you can batch it is you basically say, I'm interested in the following 5 moves, right?
Yeah, then you would have to
tell me.
look ahead for.
Well, you propose several of them, and then you basically, and then group them together and say, tell me which one of these is the best. Which you could do, right? I think you wouldn't want to. Yeah, I guess I would do it that, not looking ahead so much as like, here's just 5 possible things I could do from the current state. Tell me which one's the best. I'll do only one of them. If you tell me 3 of them are good, I don't care. I'm only doing one. You know what I mean?
Yeah. Yeah. Are there any questions online?
Not for me. Thank you. Great presentation.
Oh, thank you. Yeah.
Yeah, it was nice. Thanks. I think I understand this paper much better now.
Yeah, no, I do too.